So our next speaker will be joining online. So if we can check the link with Professor Debashis Chanda. Hello, Professor. Can you hear us?
Yes, I can hear you.
Perfectly. So thank you very much for joining. And we are very looking forward to your presentation. The floor is yours.
Okay, thank you. Thanks for the kind invitation, first of all, and sorry for not being there. I was thinking, but being bit far away across the pond, and for a short trip, in 2 days, I have to go to Monterrey, Mexico. So I could not fit the short trip to Greece. So I apologize for that. So I'll try my best to go over a new way of coloration, and already there are a few talks on coloration. So by this time we know the color is important, saving energy is important, saving earth is important. So all important parameters has been touched upon by my previous speakers. So I do not really need to go over those, but we'll just introduce myself. I am a professor at NanoScience Technology Center and Department of Physics and College of Optics and Photonics, kind of multidisciplinary appointment, just to show that optics is not just belongs to one aspect of physics, it's kind of spreading across nanoscience, physics, and chemistry. And we have a startup company, eSkin Display, in California. The startup main goal is to commercialize some of the technology being developed at my lab at University of Central Florida in Orlando, Florida. So that's kind of my little short background. And with that, let me set the tone. I think just previous speaker spoke about quantum dot-based pigments and how the pigments is destroying. This is a nice article published in 2020 in CNN article, that how, I think even she mentioned about China and India in particular, but there are Vietnam, Cambodia, many other those countries, even now multiple Latin countries like Colombia, Peru, they're all involved in creating our garments, and all the chemical we use, they dump into the water. And we need to take a pause that we are actually destroying our whole aquatic system, the earth, just because our need and hunger for color. We all looking for color of different clothes. We change our car when it looks, get faded. We change our T-shirt every few months or so because we want to have a better, vibrant color. At what cost? The cost is this, that we are making our whole environment damage just because our hunger for color. So that's, I think, enough information or motivation for scientists and all our colleagues around the world to look into that. So we looked into a special aspect, not an active semiconductor. We looked into structural color. So if you look back on this is a National Science Foundation article on our work, that if you just look at nature, they use like a butterflies, so they use structure. They do not have active pigment. Simply change of structure, they can produce all this fluorescent color based on same two material. The whole point, can I use just material A and material B and combination of that to produce all color? That means to produce different color, I do not need to look for a different molecule. And that what is advantage? Now, if I can use these two material, art friendly. In our case, we use A as a aluminium and B as some kind of oxide, say silicon dioxide, which is basically sand. So we are using an aluminium being one of the available material on Earth crust. Both of them are very eco-friendly. So we are actually trying to make these structures built based on aluminium and silicon dioxide, which is basically glass or sand. You can think about that. So the whole point is that you create color based on colorless material. Neither aluminum nor silicon dioxide has any or any oxide has any color, but you can actually produce color just like the butterfly does based on the structure, optical resonance phenomena. So again, this talk is not very commercial talk because this talk is not given by my startup. I'll be giving, so it has a little more scientific aspect. So bear with me. I will be trying to talk about little physics, not too much, but it's not a commercial talk and not a pitch, not a sales pitch, no, like nothing like that. But it's a very cool effect I will leave at the end of my talk. So what we started off, just a layman understanding that we developed a self-assemble technique where you could form this self-assembled aluminum nanoparticle on this oxide layer on a strong back mirror. So that's my mirror. And when we control all the dimension, we form gap plasmon. Again, I'll talk about in a minute in between these 1-2 nanometer gaps. And if I do so, I can actually create this kind of color. Like if I just change the dimension of these aluminum particle from say 20 nanometer, it goes from yellow to 40 nanometer to magenta red to say 60, 70 nanometer, it makes a blue color. So just by changing the dimension of this nanoparticle on the layer, we could actually change the color. And I'll show you what type of color, pretty much all kind of color we could produce, except few. So this is a scientific study that we studied the effect that this pigment can land upside down, right? So we had to create a bisymmetric. So these pigments are symmetrically grown. So the nanoparticle is on both sides so that when the pigment or this flakes will arrive, when you painted it, which I will show, that it can have different orientations. So, but making symmetric, bi-directional symmetric, you can actually make, almost angle and position independent color. And again, we studied optically that what happens. So we started with the periodic arrangement of nanoparticle, then introduce a little disorder. So what happens that the whole structural color field, all this plasmonic metamaterial, people looking for the last 3-4 photonic crystal, 3-4 decades, we could only do periodic pattern. And problem is that periodic pattern, the color is very angle dependent, means only color appear for a certain angle. And if you move your head or move the structure, you do not see the color. That was a problem. So we started studying what happened if we introduce some kind of disorder into our structuring of this nanoparticle, from a quasi disorder to a completely randomness. And we found that when we achieve closer to random pattern of nanoparticle on this 5-layer architecture, we could actually create completely angle and polarization independent color, which I will show. That is the whole goal. Again, the physics part, sake of time, I do not have time, but if there's a paper link, I'll show at the end of my talk that this is basically a physics problem, how you confine. So you can actually see this is the lights is a confined as a gap plasmon on the between these two nanoparticles. So they are basically trapped in between. So that's a mechanism. You trap the photons between these 1-2 nanometer gaps of this aluminum nanoparticle, and you form this, you absorb that portion of the spectrum, and the remaining portion comes back up, gives you the color. Now by changing the gap between them, you can actually tune the plasmon resonance, gap plasmon resonance to basically cover the whole color palette. So that's what's kind of shown here. We're just changing the nanoparticle dimension of simply aluminum. There's nothing in it. It's simply oxide and aluminum combination of engineered dimension to get the plasmon resonance right. So there is two resonance. One is this gap plasmon resonance between the gap, and there is also a vertical resonance. This is basically small narrow cavity. You couple this gap plasmon with a cavity. This is a thick mirror. It forms a cavity. You couple them, and that's the reason you're getting this vibrant color. You can produce that just by changing dimension. You can actually change the color swap. Now, when you make this pattern, we need to mix them with resin to make it a paint. So what we do, we actually flake them up. These are the kind of flakes we are looking at, that is replacing the conventional pigments. So if you take a look, these are the color from blue to say white or silver color in between other colors. So if you take a closer look, they simply have these flakes. So the flakes are about, you can control the size. We are kind of making those flakes out of these self-assembled sheet of 5-layer stack. So they all have this 5-layer inbuilt inside, and they're about 10 to 40 micron flex size, and which you can control based on the application. But the whole point is that we just by changing the this nano particle size, the aluminum size, you can produce. So this is a video just to show. So that shows that we could actually create enough quantity. 2 point I want to emphasize and show to some nice cool application based on them. One is the aspect ratio. Aspect ratio of these structures, they are only like 100 nanometer thick, and but laterally they are 20 microns. So that is about 1,000 of aspect ratio. So they're ultra light. And that because of this extremely high aspect ratio, it allows us to cover very large area. So with 3 milligram weight, we could cover say 20 square inch, which is extremely large area. Just weight is 3 milligram, but because they're only hundreds of a nanometer. What is the other advantage? The conventional paint, to get the color depth, you have to keep coating more and more layer, because we are following this Beard-Lambert law that light has to penetrate to get completely absorbed, so that you get the color depths. At our home or car, typically Ferrari coat 3 times. I was at Ferrari facility a couple of months ago. So they, let's say for instance 3 coating, so they have to make 3 coating to get the Ferrari rate. In our case, we're just 100 nanometer thick, and light does not come inside. So all the resonance is surface effect. That means it does not matter whether you keep putting more flex. It does not, light will not see that. So if you can coat extremely thin layer, we can really make nanoscale film without compromising the color depth. So the Beard-Lambert law, e to the power minus alpha d, does not apply here. We just could make extremely lightweight, ultra thin paint we can form, and I'll show some. And then this is basically shows that we, just this is the right hand panel, more of a fun as an academic guy, that we wanted to show that you can create butterfly. And you have to take a pause, that we cannot make butterfly. Even you can go to Mars, we cannot, because majority of butterfly colors come from structure dependent color. This is the first structure dependent color we can see. These are all structure dependent. It has no inherent color. Aluminum has no color, oxide has no color. Just because of structural resonance, you can create all kinds of color. And we just, for fun, we call it world's first man-made butterflies. We have a way to make them glossy. We have a way to make them matte. So this is a kind of matte color, kind of a glossy color. We have a way to just be changing the surface morphology. We can tune that, and then you can harvest those flex in a matrix, and you can paint those. Here we just, this is more of a scientific slide, and I'm not going to talk too much, but just to show that if you go to a paint shop and if you ask for a paint, they actually mix multiple base color to give you that target color. Here we do not even have a color. We're just mixing structure. So we showed just by mixing structure laterally and vertically. So we just painted color just to show what we mean. That this structure mean for magenta, this for yellow. When you mix the two structure nearby, you can actually produce all color. You can see that you can reach even blue just by putting a structure of magenta and a structure which produces yellow. You can produce a say green. And same as by making them vertically stack on top of each other, you can produce a green color. So what's the take-home message? That we actually achieved a phenomena like a butterfly does. We're mixing structure, not pigment, to create a third color. So just to show again, no time to really talk about the physics of that, but that's what the take-home message, that we have ability to mix two structure and produce a third color. Then, we are in a coating forum, and that ultimately those flakes has to be mixed with some kind of matrix so that they stay put. You will be painting. So you actually use a lot of different resin. Some known, like simple one is mixed with linseed oil for painters. And that basically a painted canvas of, butterfly. And now see the magic. Every single color on this butterfly actually is same, aluminum and oxide, but their structuring is different. If you zoom in this area with a microscope, you see those flakes. You zoom in with electron microscope, you see this bigger flakes, and then you zoom in further, you see these the nanoscopic self-assembled aluminum particle on the top. So that basically produces color, and all of the color has same thing, just that dimension of nanoparticle is changed, and you can spray up and paint it on any surface. We showed you can make on a clothes. Is important, and just to show that is important. But now there's an interesting thing we found. Now this is people already spoke about color in this forum, so do not need much introduction. That color came for this one because we are reflecting back a surrounding light and absorbing some light to produce this color, right? And that creates your visible color. Example is yellow, magenta, cyan. We are into the CYM color space. But then also we found this, because of this resonance only into the visible domain, entire infrared spectrum is reflects back entire. So that actually we showed has a huge benefit, that it does not have any absorption beyond say 900, 800 nanometer. It's simply, and all the across to hundreds of a micron. It does not have any reflection. It performs like a mirror. So what's the advantage now? So now if you can paint a conventional paint house and this plasmonic paint, and it reflects all the infrared, it keeps the surface cooler. And you can use for car, where energy is very important, for EVs, where you are saving the battery life. For cooling uniform, you can actually save a lot of, in our case, US defense, we are into all over the world, and we need to keep our soldiers cooler. And we could actually show this actual measurement that this house, about 30-degree Fahrenheit temperature difference, we can keep it cooler. And next, we actually built two houses just to, for raising fund and showing the people the actual truth. This is actually a house painted with a conventional paint. This is painted with structural color paint, and has a sensor inside, and we are measuring the temperature of the house under a given same sunlight. This is sun, simulating the lamp. And we see about 33-degree Fahrenheit temperature when we coated with our paint, which is extremely important to keep surface cooler. Moving forward, we're talking about global warming. We're wasting energy, and it's a cyclic process. We're actually damaging Earth. So that is extremely important to keep and save energy. Then I pointed out, because of the ultra lightweight, the aspect ratio of 100 over 1,000, that they are only 100 nanometer thick, and you do not need more thickness. We found that it is extremely useful for aviation industry. Just give an example that United Airlines, just removed one page out of one book. Like they have magazine in there, every flight has magazine. Just they remove one page out of every flight the flight they have, and they reported this on the information they posted, that about $300,000 and 170,000 gallon of gas just by moving one page. Sounds very ridiculous, but that's what it boils down to. And that's a Boeing 747 is a very standard aircraft. They use about 500 kg of paint. Our pessimistic, scientific concepts say, in ideal world, you need about 1.3 kg. But even if practically you'll be losing paints and all, even if you need say 50 kg, still there 10 times difference of weight, which is extremely enormous, 10 times if you consider just one page of a book. So that's a very nice article. We are the journal, they post about the prospect of this kind of paint into airlines. So, this work got a lot of interest, created a new interest about structure-based color. No active elements, no carcinogenic, no chemical, no heavy metals, like you need cobalt to grade the deep blue. Nowadays in your car, you have a cobalt. If you need a red, you need cadmium to get the red. Here, nothing of those. So you are using simply harvesting materials like oxide and metal like aluminum, which is the highest concentration of metal on Earth crust, to really produce all kinds of color. So it's got a lot of interest, created a lot of scientific interest and technological interest. National Science Foundation in USA, they covered thousands of news agency covers across the globe. So that's kind of an interesting way. Many articles came up on the commercial aspect, which you are now. So Nature Nanotechnology is one of the premier nanotechnology outlet. They actually themselves wrote about the commercial aspect of this kind of plasmonic paint and what it can do. So that kind of have a lot of promise. This is not a pitch, it's not a company and a talk, so it's more of a academic talk. So I did not really had the projection, how much this can do, comparison studies and all. But you can imagine there are a lot of interest, a lot of bigger corporation trying to work with my startup to take this to scale up process to make it cheaper and large quantity for fancy car to aircraft to houses to ships. So they have all kinds of applications they're looking at. And I'm cautiously optimistic that something may come out because of the impact it can produce in terms of energy saving, in terms of art friendliness, in terms of color based on non-toxic materials. So with that, I will stop. And again, once again, thanks for inviting me and giving me the opportunity to talk online.
Thank you. Thank you very much, Professor.